Hello, dear students. This is our next series of lectures that I am delivering on these complex analysis. जो आज का हमारा टॉपिक है that's about computation of residues. तो हम residues कैसे calculate कर सकते हैं and why we are calculating the residues, right? So first, if you remember that we have in our classwork, we have during our classes we have discussed about that Lorentz expansion, right? So if we have some function which is analytic, we can write that f of z will be equal to summation that n starts from 0 to infinity this and first series plus second one, right? So remember one thing that so if you expand that because we have this, it has the pole of the order when z equals z naught, it has the singularity exists at that point. So in this case, because when z equals z naught, so the function will not be analytic. So that means this is basically the pole for this Lorentz expansion if you define that, right? Now if we write here if n equal to अगर हम n का वैल्यू यहाँ पे 1 लेंगे, right? तो अगर हम n का वैल्यू 1 लेंगे, so it will be b1 divided by z minus z naught raised by this, right? So that means this term जो हमारी second term यहाँ पे है, जो Lorentz expansion जो है, तो इसमें अगर हम second term यहाँ पे लेंगे, तो it basically indicates that it has a simple pole at z equals z naught. Because अगर हम z equals z naught लेंगे, तो function is not defined here. We can have then b1 raised power that because it becomes indeterminate form, right? So this is very clear. So that means this second term on our right hand side, so it has a simple pole at z equal to z naught, right? So इसका simple pole है at z equal to z naught, and the residue at this pole. So residue at this pole will be the coefficient of that term. So that means जो यहाँ पे residue आएगा, that will be equal to b1. So that is basically equal to coefficient of 1 divided by z minus z naught. Because coefficient जो 1 divided by z minus z naught का है, that is b1. तो जो हमारा b1 है, that is basically our residue. So residue basically helps us to calculate that the poles of these different orders, right? So first जो ये हमारी ये एक्सपेंशन है, लॉरेंट्ज़ एक्सपेंशन, फर्स्ट टर्म जो हमारी है, इसको हम रेगुलर पार्ट कहते हैं. So this is our regular part and this is our singular part, because in second part singularity exists in this Lorentz expansion, because this is very clear, because when z equals order, so or if you take some higher orders, जैसे अगर हम n का value 2 3 लेंगे, right? So we can have then z minus z naught square r cube, or you can take higher terms, right? So that means we can have poles of these residues at different poles of different orders, right? So this is, we can say that this is the simple pole at z equals z naught, so you can calculate the corresponding residue, and that residue will be the जो यहाँ पे इसका coefficient होगा. So our coefficient in our second term, that is our b1. So that means this is how you can define the residue for the corresponding pole, or it can be simple or it can be some higher orders, right? So that means we can define them. तो हम define कर सकते हैं कि जो residue हम calculate करते हैं at a simple pole. जैसे मैंने पिछले वाले जो expression थी Lorentz expansion, तो वहाँ पे मैंने आपको दिखाया था कि मतलब at z equals z naught our function is not defined, right? So similarly we can define here that the residue at the simple pole. अगर हम simple pole पे देखेंगे at z equals z naught, तो residue हमारा होता है residue of that function fz, which is analytic. So that means which is differential at every point except at z equal to z naught. So that's, if you remember that I repeated many times how we can define the pole. So we can, the function is not analytic at that point, right? So analyticity means the function is not differentiable. So we can say that this function is not differentiable at z equal to z naught. So that is limit z tends to z naught z minus z naught f of z. तो ये किस लिए है, अगर हम कंप्यूट करेंगे residue at a simple pole z equal to z naught. Now it is not necessary, we have different types of rational functions. हमारे पास बहुत सारे functions होते हैं जो simply मतलब order one नहीं हो सकते. There can be some terms, some functions which can have higher orders, right? So in that case, so we can generalize this to how to calculate, how to compute the residue in that case, right? So then we can write the residue at a pole of order m. तो अगर हमारे पास mth terms होंगे, mth powers होगी, orders, sorry. So if we have these terms containing mth orders, right? तो उसके लिए हम रेशियो लिखते हैं, that is equal to 1 divided by m minus 1 factorial, limit z tends to z naught d raised to power m minus 1, this thing z minus z naught raised to power f of, right? तो इसका मैंने प्रूफ दिखाया था in class work, because I cannot show you the proof because I repeated it many times, where only our main focus is only on the problems related to these topics. So first I am defining so how to calculate this residue, then we will do some problems on this. So So with the help of problem, so it will be very clear, right? So first, so this is if you calculate for the simple pole, so you can write for the simple pole, so you can skip this one. Better is to remember this one. तो अगर हम ये याद रख सकते हैं कि that residue at z equals z naught for pole of order n, so that's 1 minus m1 factorial. Because अगर मैं यहाँ पे m का वैल्यू 1 लूंगा, right? तो अगर यहाँ पे मैं m का वैल्यू 1 लूंगा in this case, तो ये टर्म क्या बन जाएगी? तो अगर आप याद रखो, इट इज 1 डिवाइड बाई 1 माइनस 1 फैक्टोरियल, दैट्स 1 बाई 0 फैक्टोरियल इज 1, दैट्स 1 बाई 0 फैक्टोरियल, दैट इज लिमिट z tends to z naught, and what will be this term? D raised power m minus 1, that's 1 minus 1, so that is d raised power 0 divided by dz raised power 0, right? So this will be 1, so inside will be that is z minus z naught, and m is equal to 1 m. So that means it is not necessary to remember that how to calculate the residue at a simple pole. So better is to remember this for pole of hot rate. So अगर आपको ये याद रहेगा तो you can calculate, because then you need to put m equal to 1. So you can calculate this is basically equal to 1. So you are getting again that residue at a simple pole. Right? So this is how to calculate these residues. तो residue हम usually किसका निकालते हैं? Because we have two parts in our Lorentz expansion. So we have two parts. So first that is regular part and second is singular part. तो जहाँ पे singularity exist होती है function की, right? तो उसी का हम residue निकालते हैं, and that residue is basically the coefficient that is attached to that term, right? So that's basically a residue, right? So let's make a quick jump to one of the problem. So suppose we want to calculate the residue for this function f of z equal to z square plus 1 raised power 3 at z equal to iota. तो that means जो हमारी function यहाँ पे है, so it has singularity at z equal to iota. So where our function is not defined, right? So we need to calculate the residue at z equal to iota, right? So let us use that previous formula. तो हम ये formula use कर सकते हैं, because if you remember that इसका जो power है m जो हमारा है that is 3, right? And we need to compute the residue at z equal to iota. तो पहले हमें जो हमारी टर्म है यहाँ पे z square plus 1, इसको हमें इस फॉर्म में लाना है, because we should get some iota here, right? So I can rewrite this as, so we can write that तो ये हमारा हाफ जेड है, सो दिस वेरी क्लियर। और मुझे जेड स्क्वायर प्लस 1 को इस फॉर्म में लाना है, बिकॉज आई शुड हैव सम जेड प्लस आयोटा एंड जेड माइनस आयोटा, राइट? सो आई कैन ऐड दैट a plus b to a minus b, so this I can write as, okay, or you can rewrite this as, okay. So now the question says that, तो क्वेश्चन हमें कह रहा है कि we need to compute the residue at z equal to iota, right? So that means we need to compute that, so therefore you can write that residue at of f of z at z equal to iota. तो हमारा जो z0 है दैट्स बेसिकली आयोटा, तो जहाँ जहाँ पे हमारी फंक्शन नॉन डिफाइनेड है, और यू कैन से दैट जहाँ पे हमारी फंक्शन एनालिटिक नहीं है, और यू कैन से जहाँ पे इसकी एनालिटिक सीज होती है, तो सो देयर आर मेनी वेज हाउ यू कैन define the singularity, right? So you can say the function is not singular, or you can say that the function is not analytic, or it is not differentiable. So you can interpret it many ways, right? So that means we need to calculate the residue for this function at z equal to iota. But before that, before starting that, because our order m equal to 3 here, so that means we need to use this thing. तो हमें ये वाली टर्म यूज करनी है, दैट्स 1 डिवाइडेड बाय m minus 1 फैक्टोरियल दिस टर्म. तो दैट मींस जो हमारा m है दैट्स 3, so that will be 1 by 3 minus 1 factorial, and we can have d raised power 3 minus 1, dz raised power 3 minus 1, and this term, right? Okay, let me write first, and I can, if there will be some problems, so I can repeat it. Okay. Okay, so you can write this as, so this will be equal to 1 divided by, तो जस्ट चेक इफ इट इज राइट। सो यहाँ पे मैंने क्या किया, तो m के बदले मैंने यहाँ पे 3 लिया, दैट इज d रेज पावर 3 माइनस 1, dz रेज पावर 3 माइनस 1, एंड दैट इज z माइनस z0। तो जब हमारा z0 है, so that is iota, so that is z minus iota and power m। so just check, तो यहाँ पे इसका जो पावर m है, तो m हमारा जो है that is 3, तो into f of z, तो f of z हमारा that is this, तो f of z हम ये वाली टर्म में, right? So that means I can rewrite this term as, so this is, right? तो because z minus iota raised power 3 and f of z, जो हमारा f of z है, तो अगर you just check, जो हमारा f of z है, that's 1 by z plus iota cube and z minus iota cube, right? So that means this is very clear now. So I can rewrite this term as, अगर इसको मैं ट्वाइस डिफरेंशिएट करूंगा, तो फर्स्ट डिफरेंशिएशन विल बी दैट इज डी बाई डी z, right? Because it will be that minus 3, so so is it okay? So now it should be 9 here, huh? So what I did here, so you can write this as, because 3, okay, so this is 4, so because it should be 4 here, huh? Because minus 3 raised power 4, huh? It should be 4 here, huh? So I did a mistake. Raised power 4, and this will be 12 raised power 5. No, that's clear, because we have, तो यहाँ पे आएगा -4, so that will be -12 plus 12, sorry, plus 12 divided by z plus iota raised power 5, right? So this is very clear. Now you put that z equal to iota, so this will be equal to, that's 1 by 2 into, that is 12 upon 2 iota raised power 5, right? Okay, because iota z equal to iota, so this is twice iota raised power 5. तो यहाँ पे आएगा, तो ये 2 इसके साथ कैंसिल हो जाएगा, इट विल बी 6 डिवाइडेड बाय 2 रेज पावर 5 into I रेज पावर 5, आयोटा अगर हम 5 टाइम्स लिखेंगे, राइट? सो आयोटा रेज पावर 4 into आयोटा, सो दिस विल बी प्लस आयोटा, राइट? सो दैट मींस आई कैन गेट हियर, ओके, सो यू कैन गेट हियर, दैट्स इक्वल टू 3 upon 65, okay, 3 upon 68, so this will be the result. So this is basically when you calculate, when you compute the residue at z equal to iota. Okay, so this is because our question says that we need to compute the residue of this function at z equal to iota. So iota is basically that, it is basically the coefficient that is related, that is attached to this function, which is the third function for that singular part of this Laurent's series. Because our Laurent's series है, so that's basically this Laurent's series. This is our Laurent's series. If you check that, where is that? तो ये हमारी लॉरेंट सीरीज है, तो इसमें जो थर्ड पार्ट होगा, इसका थर्ड पार्ट जो होगा, बिकॉज एन विल टेक फ्रॉम 1 टू इन्फिनिटी, बिकॉज थर्ड पार्ट होगा जब एन होगा 3 यहाँ पे, तो दिस विल बी B3। तो दैट मीन जो हमारा B3 होगा, तो B3 हमारा, so B3 हमारा 3/65 होगा, right? Because the residue is basically the coefficient which is attached to that term, right? So that's basically what basically that residue means, right? Now there is one more problem. So if you want to determine the poles, so poles and nature of this, and compute the residue for a given function. So let me write that. So we have one more example that. And calculate the residue. So our function is that z plus 3, that is z square minus 2. तो हमें पहले देखना, फर्स्ट ऑफ हमें देखना है कि जो इसका जो सिंगुलैरिटी होगी और जो इसका पोल होगा उसका ऑर्डर क्या होगा। तो वी नीड टू चेक दैट, बिकॉज अगर डिफरेंट ऑर्डर्स फॉर mth ऑर्डर होगा लाइक 2 3 4, तो उसके लिए हम जनरल फार्मूला यूज कर सकते हैं, और यू कैन यूज डायरेक्टली, और सिंपल पोल हो गया तो वी कैन कैलकुलेट दैट है। So first, because our function is our, that is, so our, so we can write that f of z equal to, so that is z into z minus 2, because I can rewrite this way. Now we can check easily. The first singularity exists are poles. So इसके poles होंगे. First it will be at z equal to 0, and second will be at z equal to 2. Because we need to first calculate, determine the poles. पहले हमें देखने की poles कहाँ पे होंगे, poles क्या होंगे, and उसके बाद हमें calculate करना है residual function का, right? So first you write now the poles for this function. Poles of f of z. तो पोल्स हम कैसे लिख सकते हैं, सो दैट मीन जो हमारा डिनोमिनेटर होगा, तो ये हम ऐसे भी लिख सकते हैं, बिकॉज इफ यू पुट दैट डिनोमिनेटर इक्वल टू 0, सो दैट आल्सो गिव्स यू द पोल, राइट? और यू कैन राइट डायरेक्टली that z0, what should be the value of z0, so that's the corresponding pole to that function, right? So or you can write this way, that so z equal to, either z equal to 0 or z equal to 2, z equal to, these are two symbol poles for this function f of z, right? So as so you can, where the function is not defined, we can say that, huh? Now if you calculate, now what will be the this residue at, so first you calculate that residue of f of z at z equal to 0, so that is limit, because, तो आप यहाँ पे देख सकते हो, बिकॉज जो हमारी फंक्शन यहाँ पे एफ ऑफ जेड है, तो जो जेड, बिकॉज दिस यू कैन राइट दिस टर्म, तो इस टर्म को मैं लिख सकता हूँ, आई कैन राइट दिस एज दिस वे, दैट इज जेड प्लस 3 जेड माइनस 0 इनटू जेड माइनस 2। तो इसको मैं ऐसे भी लिख सकता हूँ ना, तो आई कैन, ये टर्म मैं ऐसे भी लिख सकता हूँ, दैट इज बिकॉज जेड आई कैन राइट एज जेड माइनस 0, सो दैट मींस at z equal to 0, so we have the poles where the function is not defined or where the singularity exists, and second is that z minus 2. Okay. Now क्योंकि हम दोनों अगर हम देखेंगे फर्स्ट वाली दैट इज z minus 0 it has a simple pole because its power is 1, right? So that means m equal to 1. So you can write directly that that residue at a simple pole at z equal to 0, so that is z minus z0 f of z. Now f of z is because we have this limit that z tends to 0. That's minus 1 by 2 because z equal to 0, so this is minus 1 by 2. So this is the pole corresponding to z equal to 0. And similarly, जो हमारी second term है तो आप देख सकते हो यहाँ पे जो हमारा second pole है that exists at z equal to 2, but that's also a simple pole because जो इसका power है that's 1, right? So this is very clear because so I can write the residue at a simple pole, right? So using the general formula or simply the residue at a simple pole. So better is to write for the general formula because you can generalize that because for this m equal to 1, so it will reduce to the residue at a simple pole, right? Okay, you can rewrite this as, now you write this as uh, residue of this f of z at z equal to 2. So that's equal to okay, or you can rewrite this as that's 1 by 2 because z equal to 2, so this is 1 by 2. So हमने calculate किया residue at both the poles which are simple at z equal to 0 and z equal to 2. So this is how we can calculate these computation, how we can compute the residue. And similarly, there's one more that we can again calculate the compute the residue at z equal to infinity, right? So in that case, so this is a little bit different. So you need to calculate the the Lorentz expansion. You need to write the coefficient that the second term that's 1 by z term has. So that's basically the residue for that term, right? But at z equal to infinity, right? So I will show you one example. So it will be clear. Okay, so you have this. Suppose we have one more problem that you need to find the residue at, or you can write that residue of this function. So you need to find the residue of. So z cube upon z square minus 1 at z equal to infinity. तो हमें infinity पे इसका residue निकालना है, right? So how you can solve this? So first you can write that let f of z z square minus 1. Okay. और इसको मैं लिख सकता हूँ because we need to find the residue at z equal to infinity, right? Or you can rewrite this as that is this will be equal to right? तो इसको मैं ऐसे भी लिख सकता हूँ because you can use that Taylor series expansion. This one minus t raised power minus 1 that is t raised power n, or you can expand it this way, right? इसको मैं further simplify कर सकता हूँ because we need to multiply that z, so you can add that z plus 1 by z plus 1 by z, right? तो इसको मैं लिख सकता हूँ because I can multiply z, so this will first term will be z because यह आपको z multiply करना है to each of these terms, right? तो हर किसी term को multiply करना है z, so this will be z plus that's 1 by z plus 1 by z cube, right? Now जो इसका रेजिड्यू होगा, so रेजिड्यू हमारा जो होगा that is minus टाइम्स, तो जो इसका रेजिड्यू होगा, so we can write that residue of this f of z at z equal to infinity, so that's equal to minus times coefficient of 1 by z, right? जो कोएफिशिएंट किसका होगा 1 by z टर्म का, राइट? तो जो कोएफिशिएंट 1 by z टर्म का है, तो आप देख सकते हो यहाँ पे, तो आप यहाँ पे देख सकते हो कि जो कोएफिशिएंट 1 by z का है दैट इज प्लस 1, राइट? बिकॉज़ यहाँ पे कोएफिशिएंट इसका 1 है, and that basically gives us the residue at z equal to infinity. So that's equal to minus into 1. So that is right. So these are some of the problems that which are related to how to compute the residue. And in our coming lectures, we will discuss about so how you can use that Cauchy residue theorem. So you need to define अगर हमारे पास कोई function होगी, so because there can be more poles, so there can many poles which exists for a given for that analytic function जहाँ पे हमारी function define नहीं है, तो we need to compute all those residues, and so Cauchy residue theorem says that if we calculate that sum of residue, that should be equal to 0, right? So hopefully in our coming lecture we will take some problems on this Cauchy residue theorem, and some problems related to those proper and improper integrals, right? So hopefully, so this will benefit you in your competitive exams. I think I should stop now. Thank you very much.